Hello and welcome. Today we'll be presenting our project titled Detecting AI-Generated Images, a Neural Network Approach. This project was completed by Group 39, including Shail Patel, Rushal Narendive, and myself, Devanshu Shah. The goal of this work is to address the growing concern of distinguishing real images from those generated by artificial intelligence. Coming to the next slide, so with the rapid advancement of generative models like Stable Diffusions and GANs, AI-generated images have become increasingly convincing. This raises challenges in digital media integrity, cybersecurity, and misinformation detection. Traditional forensic techniques are no longer sufficient, prompting the need for robust machine learning solutions. In our project, we developed a neural network-based approach to classify real versus synthetic images. We use the CIFIC dataset for this study. It consists of 1 lakh training images and 20,000 testing images, equally split between two classes, real and fake. Real images were sourced from the CIFAR-10 dataset, while fake ones were generated using the Stable Diffusion version 1.4, a state-of-the-art model. Its structure takes it an ideal benchmark for studying AI image detection. Each image in the dataset is labeled as either real or AI generated. We applied normalization, resizing, and data augmentation during pre-processing. The final classification output includes a label and a confidence score. Additionally, we employed GradCam for visual explanations, allowing us to interpret the model's decision-making regions. Performance was evaluated using standard metrics, including accuracy, precision, recall, FN score, and ROC area under curve. About the baseline model, we begin with a baseline convolutional neural network. It consisted of convolutional layers with ReLU activation, batch normalization for stable training, and dropout to mitigate overfitting. The final classifier used a sigmoid output. The model was trained using the Adam optimizer with binary cross-entropy loss across 10 epochs with 5-fold cross-validation. On validation data, the baseline CNN achieved a precision of 94.45%, recall of 94.98%, and F1 score of 94.70%. On the test set, it attained an accuracy of 94.39%. The ROC curve and confusion metrics highlighted good model performance, though we saw room for improvement, especially in reducing false positives.
We implemented a transfer learning approach using ResNet 50. This 50-layer deep residual network is pre-trained on the ImageNet, and it serves as a powerful feature extractor. So we resized the inputs to 224 cross 224 dimension and normalized them. We froze most of the pre-trained layers and only fine-tuned the final residual block and the custom classifier head. So the new head consisted of fully connected layers with ReLU activation, dropout, and a sigmoid output. Going on to the evaluation of this model, so we saw significant upgrade in the result. So on the validation set, we achieved an increase in all the evaluation metrics. The ROC curve and the confusion matrix visually confirm the model's robust generalization, and the false positive are also reduced compared to the baseline model. The ResNet 50 model demonstrated stable conversions. Training loss steadily decreased while the validation loss plateaued early, so which indicates no overfitting. Evaluation metrics confirm the model's capability to minimize both false positive and false negative. The initial training epochs showed rapid improvement, and dropout regularization further ensured model's stability. Transfer learning proved especially effective for the classification task with limited training data. To understand the model's reasoning, we used GradCam. This method generates heat maps showing which parts of an image influence the prediction most. So as you can see in the real image, more focus is given on the object, whereas for the AI-generated image, more focus is given on the background. Our model occasionally misclassifies due to common CNN issues. It favors textures over shapes and sometimes misses key objects, as in this example, it misses the bird's head. Other differences in real and fake images stats can also mislead. Finally, it can be overconfident on weak visual hints. So these highlights areas for future improvement.
The following can be the future model improvements. Data augmentation techniques such as adding blur, jitter, and rotations to prevent shortcut learning. Focal loss and hard negative mining can be done to handle tough class cases better. Fine-tuning deeper ResNet layers can be done to learn task-specific patterns. GradCam auditing can be done to ensure the model that focuses more on the meaningful parts. Attention layers can be added to guide focus towards the object structure, and self-supervised pre-training should be added, such as SimCLR, BYOL, label smoothing for robust feature learning. Our team has strong experience in computer vision and deep learning. We have worked on an image captioning model combining ResNet 50 and transformers last semester, achieving high blue and sky scores. We have also built CNNs for digital and object classification using datasets like MNIST and CFAR10, and have experience with object detection using YOLO V5. These prior projects helped shape foundation for this work. We would like to acknowledge the SciFec dataset contributors, as well as the original paper on SciFec provided valuable insights that guided our methodology. Thank you for your time and attention.